I figured out a way to do a pattern of how to actually figure out how to name these properly. You'll notice, though, with the ionic bonding, there's a lot of rules with it. Big time. All right, so there are 3 types of bonding. How to identify ionic bond, just like what we were doing, metal plus a nonmetal. So everything you just did, all 7 examples you just did on that little sheet, the thing, those were all ionic. Go ahead and take a look if you want. You had calcium, that's a metal. You had sodium, that's a metal. Okay, all those were metals that you had on the left. They were bonding to a nonmetal, which was on the right. Those had a negative charge. So when you have opposite charges come together, you're going to have an ionic bond. Okay, covalent bonds, however, is nonmetal with nonmetal, and so when they come together, they share electrons. So that naming scheme we're going to cover like a couple days before the test. And last but not least is actually the easiest, metallic, because there's really no naming scheme for metallic. We just call them alloys. All right, so let's talk about what ionic bond is, metal plus a nonmetal. So let's go through some wording things real quick. They did a little hippie version. They say it's formed by the transfer of electrons. That's the correct definition. Here's my definition. The nonmetals are stealing electrons from the metals. That's why I have a little thief down there. But see, it's okay. He has a smile. You know.
He's happy he got away.
All right, so anyway, a positive charge is attracted to a negative charge. This is how it's always going to work. Now, again, let me show you exactly what's happening again. All right, so what's really happening is this. This is a perfect picture because look what happens. 1 valence electron, 7. They both now have 8 because what happened was he gave it up and dropped down to the lower level. That's why it works out every time. You are satisfying the octet with both of these guys. The only thing is, though, now he's chasing this one down because negative charge, positive charge. It's just natural. Now, notice this over here. We call them atoms, but when they lose or gain a charge, they become ions. And then when they actually come together and make the bond, they become sodium chloride. Notice there is a naming different scheme for each one. If they're by themselves, they're an atom. If they have a charge, they're an ion. When those ions finally come together, we put them with their bonds, which is the sodium chloride. Okay, so anyway, ionic bond, basically, if you didn't hear anything I just said, basically that's what it just says at the very bottom. And we're always going to talk about salt. Salt's like one of the basic molecules out there. However, water is more of a covalent bond. That's a nonmetal, which is hydrogen, bonded with another nonmetal, which is oxygen. And so this is where we left off yesterday. We were talking about bonds formed when the sharing of electrons. They're coexisting. However, and some of y'all, and I like this little picture of the lady in the tramp. But anyway, you ever go out on a date and they say, hey, let's get a dessert. Let's share a dessert. And I'm like, get your own darn dessert. But anyway, it's like, no, I just want a little bite. And then all of a sudden they just like, it was apparently a bite from a shovel. So even though this is sharing, sometimes you might share something, but it's shared unequally, and then it's shared equally. And so therefore, we have 2 types of covalent bonds we got to talk about. So 2 of the types of covalent bonds, and if you got your other periodic table out, we're going to talk about the electronegativity. That's the only reason why we're going to look at that today. And this is actually going to be a little small segment we got to talk about. But there are 2 types. There are nonpolar and then there are polar. And how I remembered this was nonpolar, no pull. In other words, they're kind of canceling each other out. And then polar, I think, a pull. And that's easy to remember. That actually makes sense for once in chemistry. Something actually goes along with the name. Nonpolar, no pull, polar, pull. And that's really what they mean. So when they are shared equally, they are nonpolar, which means they're canceling each other out. Okay, they have the same strength, they're pulling against each other, and they're, it's like the Incredible Hulk versus the Incredible Hulk. Okay, he's going to cancel each other out. However, whenever there's a polar bond, though, someone's getting a little bit more piece of the cake than the other. They're sharing, but they're sharing unequally. It's kind of like an oxymoron, but it's not really. So I'll go ahead and give you a quick rundown. The difference thing here, and I'm going to show you some quick samples on the board. And this is going to be real fast. So you remember those little numbers of electronegativity in the bottom right-hand corner I told you about your test earlier in your periodic table? Yeah. Okay, we're going to look at some of those. Basically, when I say En, I'm talking about electronegativity difference. Okay, which means if I say what is the difference between what I have, you're going to subtract, right? Okay, so that's what you're going to end up doing. So again, a quick review here. Nonpolar covalent bonds means no pull, when electrons are shared equally. In other words, one is not better than the other. It's actually perfectly 50-50. Okay, so I always like to look at it as a tug of war. They're kind of balancing each other out. Okay, but remember, less than or equal to 0.4. So for example, oxygen has electronegativity of 3.5, and this is O2. So one on the left is oxygen, one on the right is oxygen, but they're sharing that electron bond. So the difference between the two, if you look it up, 3.5 minus 3.5 is going to be 0. That falls within the less than or equal to 0.4. So when we do polar, which is pull, they are shared but unequally. So in other words, their difference is one side's going to be a little bit stronger than the other. The other guy's putting up a fight, don't get me wrong, but it's not enough to make a difference. So this is the one I want to talk about actually, because when you think polar, the word polar, this should be the molecule that comes to mind. And no, not Mickey Mouse, but water. Okay, water is the most polar molecule out there. It's the most plentiful. It's the reason why it dissolves everything almost, except for oil, because those are nonpolar. We'll get to that later. Anyway, so what I'm talking about here, if you're trying to find the electronegativity of hydrogen and oxygen, notice this. They did not multiply, this is hydrogen's electronegativity, the 2.1. Notice they did not multiply it by 2, but we have 2 hydrogens. No, they only care about one bond. If it's identical over here, doing it twice would just be ridiculous. Why do twice the work? So you're just looking at one type of bond in between the two. So in other words, don't multiply on this one, guys. Okay, just take one element minus the other and you'll be fine. Okay, any questions there? That's actually a good picture up here, how they have to show the sharing. They're unified together, they're both happy. Anyway, so 1.4 actually falls between that 0.5 to 2.0 range. We did covalent bonds. That's the only two you got to know. Now, when it comes to naming the covalent bonds, we're going to get that later. There's no difference between polar and nonpolar naming. Metallic bonds, however, are going to be metal plus metal. Those are not hard to name at all. We just call them alloys. And they're easy to identify. If you see a metal with a metal, you know, like you're actually sitting on an alloy right now. You don't realize it, but you are.
That's my butt.
So, yeah. I just now got what you said. Anyway, bonds found in metals holds metals together very strongly. The form between atoms of metal, metallic elements. The electron cloud around the atoms are actually kind of just there, but they're so dispersed equally that the bond is strong. This is one reason why they're great conductors. Notice that we put metal in everything. So any examples here is sodium, iron, aluminum, gold, cobalt. You know, take your pick. The majority of the periodic table is metals. So by the way, when you shock yourself on a metal, that's what's happening. Those electrons are moving so fast because guess what? Metals are positive, and they're going to zip right past you. Okay, so real fast. Ionic bonding is what we're mainly going to be talking about for the next week. It's going to be interesting. So metal plus nonmetal, there are two main types, and then we're going to break them down even further in their naming. Let's talk about the binary real quick. Binary is very simple. The basic ones y'all were doing yesterday. They make sense. They're nice. They're great. NaCl, Kf, MgCl2, MgO, Ca3, N2. We talked about how to make these. You crisscross the charges. Okay, that's not too tough. However, today we're actually going to take it a little bit more old school and work our way into the why we do the crisscross. Because if you understand why we do the crisscross, then the next part's going to be easy. But anyway, notice this though. Please do remember metals on the left, negatives on the right. So those are binary. That's just a sample, and we're going to go back over it again next week. But remember that how I showed the periodic table. Notice that the positives are on the left and the negatives are on the right. That's a good way to actually remember that as you read from left to right on the periodic table. Polyatomic ions, though, are 3 or more. And I gave you this polyatomic ion sheet. How to know, and this is how you need to differentiate, am I dealing with a binary or poly? If you're dealing with a poly, you have at least 3 or more different elements up there. Notice I said different. The subscript don't count. I'm just now picking that up. All right, so we're just talking about binaries, and we're going to talk about without transition. So we're not including these guys in the middle right now. We're just going to look at these metals right here, bonding with any of these gals over here, okay? That makes it very easy. So if it is not a transition metal, the name of the metal and the nonmetal are listed just in order, metal first, nonmetal. But I told y'all this yesterday, but now I'm giving you the note for it. Nonmetals change their last name. So you don't say sodium chlorine, you say sodium chloride. Same thing with all these other guys. In fact, let's practice it really, really fast. Name these guys. Double check your answers. Be sure you spelled them correctly because spelling does count a little bit. So on the first one, you got sodium chloride. The next one, you got sodium oxide. Notice you're just adding IDE. Lithium chloride, calcium oxide, lithium nitride, not nitrate.
Why is it not nitrate?
Because trait is NO3.
So it's like ammonia nitrate?
Right. Because in binary, they don't get 8 or 8. That is actually very, very important.
Fertilizer.
That's why I put that one up there. If it was carbon, you don't put, carbonate or ite, because that's like CO3. So it does depend on those things. So on your polyatomic ion sheet, do realize this. I'm reminding you, okay, to receive credit, I don't have to see this right here, but I have to see on one side this and the other side the formula with the sign. Do not forget about the sign. Yes, it's very tiny and it looks like it's just a dash, but that dash is very important. That's the charge. So I'll go ahead and tell you what polys are. They're just compiled elements together, and you treat them just like one element. Okay? So for example, NH4 is ammonium. Treat it like an element. In other words, it has a +1 charge. So when we do bond it with stuff, you do crisscross the charges, but remember to keep all these guys in parentheses, and you're going to see me talk about that here in a little bit. But FYI, just remind you about the cards. That's how it's going to work. On the polyatomic ion bingo, what we're going to do is I'm going to do the same thing. I'm going to have some names and some elements and stuff like that. I'm going to draw random cards, and then you're going to mark off on your bingo card which one's which. However, if you don't know them, then it's going to be kind of hard to mark them off. All right, so anyway, number one, y'all working out through all these, do realize your test is going to look like this. And when I mean it looks like this, it looks like this. Now, do realize when I told y'all, when you do answer these, it's mainly going to be like answer the following. In other words, if I give you the formula, you got to give me the name. If I give you the name, you got to give me the formula. What's hard about this is the multiple choice, because as soon as you look at this, you look at multiple choice, and then you get confused. And then you start second guessing yourself. I'm going to warn you right now. Cover up your answers when you do these multiple choice parts. That's my second warning again. I've said it last week. I'm saying it again. I'll be saying it every day until the test. People have done a lot better when they have covered it up and then did the work and then answered. Because, trust me, I put every possible option you could to screw up down there. Yes, very evil. All right, so what is the following compound? Well, if you take a look, it's an ionic compound. So we say potassium and then chloride. So remember, the whole naming scheme for this one, there wasn't something we haven't gone over transition or anything like that yet. So it's very basic. The last guy just can't say chlorine. It's got to end in IDE. So which one of the following does follow with that? B. Would be B. This is chlorite. That's a poly, which is on your polyatomic ion sheet. Do you realize, and I'm squishing this now, that this is chlorite and chlorate. These are all polys. If it ends in ite or ate, it's a poly. It's one of these guys. It means multiple ions. This right here is just 1-to-1. That's binary. So all binaries will end in IDE, never in ite or an ate. Okay? All right, next one. It said, what is the formula of the following compound? Magnesium phosphide. Well, don't even look at your answers. You got Mg, okay, and then you got phosphide, which is really what element? Phosphorus. Do you realize that is not phosphate? Okay, phosphate is this guy. You see the difference. You do need to start figuring out what's the difference between an ate, and IDE, because if you don't, that's where everybody will fail at. I'll go ahead and tell you, people who get things mixed up is the phosphate, carbonate sometimes, sulfate, sulfite, because they think it's sulfur. What's another one that people, oh yes, these, and of course the chlorates, chlorites, and all that. Those are the ones people usually mess up on, because they think, they see sulfur or phosphorus, and they think, okay, well that's SO4 or something like that. That's not true. There's a big difference. Okay. So phosphide means it just has like one piece. So what's the charge of your Mg? 2. And what is your charge of your phosphorus?
-3.
So when you crisscross these guys, drop the signs, you should have a Mg3 P and then the 2 on the outside. So which one of these do match that? C. Okay, so see what I'm talking about? If you work them out before you answer them, you'll get them right. If you go in guessing, you're going to make a 30 on the test, and that ain't going to help. And yes, I will tell you, they do make 30s. What is the name of the following compound? BaCl2. So first off, is it binary? 1, 2. 2 parts, just like this one up here. 1, 2. All right, so it is binary, so it has to end in IDE. Does that 2 really matter? No. It's an ionic compound. This isn't a covalent. We haven't got there yet. We're talking about prefixes. So you just say the name, barium, and Cl, which is chloride. And of course, I always have to look back up and figure out, does the L come for the H? I was about to write the ID. All right, so that's when you have to look. Now, however, I did kind of put an extra one in here. Ooh. A lot of people want to go to this like, oh no, it's a prefix. Well, it does mean 2. We should pick it. First off, I'll go ahead and tell you, we'll never use bi, even though we said the word binary compound. That's just to mess with you. We have not even talked about transition yet. So you only had 2 choices up here, these 2 guys. I'll go ahead and tell you. Technically, you're supposed to have the second one lowercase. Okay, technically. So I will bring that up from time to time. I'm not going to do too much of a stickler on the test about that, but I did want to bring that up because that is something more professional. All right, so last one. What is the formula of the following compound? Beryllium oxide. That is binary. It ends in IDE. So beryllium is Be, and oxide, which is really which element? Oxygen. And so we just have to do our crisscross. What's the charge of beryllium? And what's the charge of oxygen? Oh, like charges. We crisscross these. You do end up with Be2O2, but what else you got to do? Simplify. Do y'all rather have the word simplify or reduce? Okay, simplify, reduce. I'll say them both. So which one is more correct? This one. So these are the possible ones we've gone over so far. And I will tell you, a lot of people, and this one was mainly meant for this issue right here. People forget to reduce. This one I'm not too much worried about. Some people just start picking random ones because they don't know what they're doing. Over here, people just forget to crisscross charges, and sometimes they just drop them down. There's no dropping. You got to crisscross. This one was just making sure you know the difference between your polys. So all type of questions. This is just a big warning of how I can start asking these kind of things. I go over this stuff to kind of start helping you out. That's why I do see how people do get confused with the sulfate and I. All right, 2 binaries. Now we got to talk about how to deal with transition metals, okay? This is where, now we're still just doing binaries. We're not adding polys in yet. All right, I already gave you a little bit of prequel to that. We'll do that tomorrow. But transition metals, well, to me, they take a little bit more thought. It's not so cut and dry, you write them down and you're done. You actually got to figure out the charge of these guys. Let me say that again. You have to figure out the charge of these guys. All these guys get a Roman numeral, except for 2. And that's going to be zinc and silver. And I'm showing you a chart here a little bit. Okay, so write this down. This is very important. Okay, I gave you 2 forms. I gave you the long and depth version for those of you who like everything written down. And then I have my shorter version. I like my shorter version. By the way, if you don't have your periodic table out, it might be good to take it out and start writing some of these down, like on there. For example, zinc and silver, I would go ahead and label those guys that they do not get a Roman numeral. We know their charge. Zinc is always +2. It'll never be +1, never be +3. It'll always be +2. And silver will always be +1. And I'm going to show you a trick how to memorize it. And it really takes, if you know the charge of aluminum, then you can figure out the charge of these guys. Actually, I'm going to show you the periodic table here in a second. So more focus on writing these down. All right, so Roman numerals for all transition metals except for zinc and silver. They are in the transition metal column, but they do not get a Roman numeral because we know their charge. Do the alkali metals and alkaline earth metals get a Roman numeral? No, we know their charge. This charge is always +1. This charge is always +2. It's the creamy filling we got to figure out the charge of. Now, here comes raise the question. Well, tin and lead. Oh, well, tin and lead. Okay, well, they're over here in carbon's family. We treat them like transition metals. I know that's confusing. But yes, they get a charge. Most of the time it's either +2 or +4. I'm sorry, but that's how it has to be. So basically, the way we like to do this is if you remember that little stair-step line, anything that's a metal gets a Roman numeral, except, and it's easier to remember the except, alkali metals, alkaline earth metals, aluminum, zinc, and silver. Bing, and you're done. And that's why I like the short one. Now I'm going to show you a picture that makes things a lot better. So remember, I had to put it in. All of the other metals must have a Roman numeral. In other words, basically everything that you see is in pink right here gets a Roman numeral except the ones that are currently labeled. Okay? So I would say label these guys right here, the numbers that you see, and that is true, they're within the right column, but these guys will never get a Roman numeral. I put a star, something that you can do to remember those three, because you should automatically know these two groups do not get a Roman numeral. You should by now, because we haven't been writing calcium with a charge, and we never will. It'll always be +2. But everything else, including these nasty little F block down here, they get a Roman numeral also. But I'll only ask you probably about uranium. So anyway, +3, aluminum is always +3. Well, just go down the steps. +2, which is zinc, and then +1, which is silver. And you're done. It's not hard. So 3, 2, 1. I think you could do that. This is a very good chart to study, by the way, to remember who gets a charge or not. By the way, metalloids, nope. We don't deal with those in terms of charges, so don't worry about that. But I will tell you, remember tin and lead are right here. These two guys, they get a Roman numeral. So let me zoom into this, guys. So pop quiz question here. Oh, I wish I could zoom back out, but you could see. Okay. Notice this. So, about to say silver. I don't know why. But sodium. Notice we say sodium ion. We don't say sodium with a +1 charge. We don't say sodium 1. We don't say zinc 2. Okay? We know their charges. Again, back on the periodic table, zinc's right here, and sodium is right here. Okay? We know their charges. They're always a set number. But when we talk about transition metals like copper, iron, manganese, and tin, all these guys in here and then these two guys over here, they have to have a Roman numeral. They can change their charge. Iron can be +2, it can be +4. Copper can be +2, it can be +1. Manganese is usually going to be +7, but it can change its charge too. Tin can be +2 or +4. They change. And that it really depends on who they bond to. It's how much they've been oxidized. So anyway, this is where I'm going to break this down. This is where knowing the different charges, and I like doing this example because this puts everything in perspective. All right, look off to your left right here. You'll see 4 different formulas, but you'll notice something. What do they all have in common?
Oxygen and iron.
Oxygen and iron, okay? Here's my question. Does oxygen's charge ever change? No, it does not change. However, iron, since it is one of these transition, he can change his charge. He can do what he wants. He's a honey badger, okay? Now, however, the naming scheme still works out. The same thing, we still put IDE, okay, on the second guy. However, since this is a transition, you have to have a Roman numeral. Okay, I said that slow. You don't have a choice. Because if you write down iron oxide, well, I'm going to say, well, which iron is it? Is it iron 1, iron 2, iron 3, iron 4? How to do each one of these guys, all right? So if I give you the name, you got to be able to give me the formula, and if I give you the formula, you got to go back to the name. By the way, to practice this for the test, if you do these worksheets forward and backwards, in other words, check each of your answers forwards and backwards, you will be ready for the test. There's nothing I can't throw at you that you wouldn't know, except for throwing down a calculator. Okay, so let's take a look at this first guy. So, exclude the stuff at the top for the second. I give you Fe2O. All right? And you don't see them up here and all this other kind of stuff, but that does kind of help out. Here's the main thing. All bonds or all compounds have to equal what? 0. Okay? That is how it's going to help you out figure out solving this. Okay? It's just like algebra where you had to have your x and figure it out. Yes, you got to find your x, unfortunately. I know, right? But anyway, here's the good news. The second guy, you're always going to know the charge of because he's going to be a non-metal, and you know the charge of oxygen. It's always -2. It's never anything else, so that helps. The other thing is that people mess up on is knowing what to do with the subscript. I'm going to tell you, the subscript is basically a coefficient. And so all you do then is just set it up to solve. Now, I've had many people do it in their heads. I'll tell you what, you figure out your way and you work it. But I'm going to show you like 2 different ways to work this out. And you pick your way, which way you like the best, okay? I will tell you though, the reverse crisscross is not a good idea because 50% of the time you will miss it. And trust me, I have them on the test where, I mean, you could do it on this one and get it right, but that's only because it's not been reduced. If it's been reduced or simplified, you can't do it. But anyway, just like we talked about earlier, we don't know the charge of this guy, but we know there's 2 of them. And each iron gives off a charge, okay? If it was a +2 charge times 2, the total charge then would be 4. If it was +1 and there's 2 of them, then the total charge would be +2. So we're trying to figure out what fills in the blank here. Now, a lot of y'all could just start plugging things in and then figure out if it equals 0. That's usually one way people do it. Otherwise, you could just solve for x. You could just look at this. Basically, what I'm saying here, what times 2 minus 2 will give you 0?
2, 1.
1. And what 1? A +1, okay? And so that is actually the big difference. So if you plugged in a +1 here, +1 times 2 would give you +2. Subtract -2 gives you 0. That's your charge, and that's what you're looking for. So what do you do with that number? Well, you put that as your Roman numeral. And let me go ahead and tell you, if you don't know Roman numerals, you might want to go back and study up on it. I digress because they used to teach Roman numerals. Now I don't think they teach them anymore. But in case you've just been living under a block or a rock.
How high do we need it on?
8. 7 really, but let's say 8. 4, let me just go up to 8 for you. That's 5. So here's the other way of doing it. If you want to kind of rearrange some of the stuff, you can do this also, just like I did on the board over here. The 2 came from the subscript that was the 2 at the bottom of the iron. Okay? X is always going to be basically whatever the element you're trying to find is, which is going to be a transition, and yes, it's always going to be on the left. I will tell you, it'll always be on the left. You'll never have to plug in a negative here. I promise. I swear. Okay? So when we do that, we take iron, whatever the charge of that iron was, which was +1, well, that's going to be the Roman numeral. So then you would write it just like always, iron oxide, but in between you got to put the iron in here. Oh, by the way, let's say you get lazy and you say, well, I'm just going to put a 1 here, a number 1. I will count that off in a heartbeat. Do not put normal numbers. It has to be Roman numerals. Has to be. You have no choice. So this one's easy to do. When they're 1-to-1 ratio, there's no multiplying. But y'all can glance at this without doing any algebra and actually tell me what the answer is. What's the charge of this guy? Yeah. What minus 2 will give you 0? +2. Another way of looking at it, this is the algebra way. You know, you could have x plus -2, but -2 will give you, and then you basically just solve for x. And that's like one of the easiest algebra problems ever. So that iron would be iron 2. Okay? We are going to work some of these backwards, though. We'll go over that. The backwards part's not hard. It's going to this, which is the hard part. Okay? Let's try this one. So basically, this is just like that calcium one I showed you earlier. It works exactly the same way. And I'll go ahead and tell you that you'll either get this little schematic or something like that. But basically, as you go through this, you can actually take a glance at what you need to do. So basically, what times 2 minus -2 times 3 will give you 0 is basically what it's going. Now, where am I getting everything from? Well, first off, the question mark is we don't know this guy. The 2 that I got up here comes from the subscript. I know I got to multiply this by 2 because each iron is going to give off a charge. I need to know how much of each charge is going to be. The -2 is coming from the oxygen, which you should know by looking on the periodic table what its charge is. And that 3 right here is coming from the subscript of the 3. And that's pretty much it. So when you take 3 times -2, you get -6. So then basically you're trying to figure out what times 2 minus 6 will give you 0. You already kind of know the answer to that. It'd be 3. This one you might actually have to put down in an algebra kind of way. You might have to. Unless you know some other shortcuts that kind of help out. Yeah. Okay. Any questions on that? Again, now's a good time to start slowing me down. So iron 3, right here, that's what it would be. All right, you're starting to see a pattern here. You should be. Now, iron 4, how do I know this is 4? Well, it's very simple. Basically, what minus 2 times 2 will give me 0? Or basically, well, 2 times negative 2 is going to be negative 4. So what minus 4 will give you 0? 4. Same diff always broke down. Again, there are two ways you could do this. Some people have created their own way of working it out. But I will tell you, reverse crisscross will not work on some of these guys. For example, it won't work on this one. Well, why not? Well, look, if you put that 2 over here and that 1 back over here, you're saying that that iron then is iron 2. But that's not iron 2. Iron 2 is this guy. Okay, there is a big difference. I'm warning you right now, if you reverse crisscross, it's going to hurt. Unless you knew that you need to make everything back equal to the negative 2 here. Anyway, I digress. All right, iron 4. So how to work some of these guys backwards. That's what we need to work out now. So we know how to go forwards, which is the hard part. Backwards is easy. Let's say I gave you iron 1, iron 2, or iron 3, or iron 4 oxide. You just have to put the charge above their head like you normally do. And you're like, well, I don't know the charge of iron. Yes, you do. What does that Roman numeral tell you? The charge. That's plus 1. That's plus 2. That's plus 3. That's plus 4. Don't ever tell me you don't know the charge of a transition metal. What?
It's October 1st. Is that the due date or the day we do
The white shirts.
Oh.
What day?
All right, go ahead, check your answers here. So, by the way, all these were transition, by the way, since we just did transition. But none of them were polys, so you're still in an IDE. Now, usually what I do, guys, I name it normally, but then I go back and I add in this part, because it makes it just a little bit easier. So, on the very first one, when you're trying to figure this guy out, what is the charge of bromine? Well, let's find him up here. He's in this group. So what charge does bromine have? Negative 1. Okay. Well, if he's a negative 1, and there's 2 of them, the total charge on this side is negative what? Hold on. Let me do this. The total charge is what? Since I was just writing down the answers, not listening.
2.
Negative 2.
Negative 2.
Okay. Well, then what does the charge of this guy got to be to match that negative 2?
2.
It has to be 2 also. Okay? Same thing down here for, so this is copper what?
Copper.
Copper bromide.
Well, copper what? Bromide.
Bromide. Copper 2 bromide.
Copper 2 bromide. All right, nickel, however, this one should be easy. What's the charge of the oxygen? What?
Negative 2.
Yeah, when he gets back in. Negative 2, so what's the charge of that nickel got to be? 2, so it should be nickel 2. Down here, nitrogen has what charge? Negative 3. So what does the iron got to have?
3.
Okay, now last one is you got some subscripts. You're going to have to do some dividing. What's the charge of the sulfur?
Sulfur.
Negative 2. All right. However, we don't know the charge of this guy, but we do know there's 2 of them. So each one gives off a charge. So you either got a choice here. Is this going to be plus 2 or plus 1? Well, basically, what times 2 minus 2 will give you 0? Plus 1. So that's why this one is going to be a 1 right here. So going down the line, you should have copper 2, nickel 2, iron 3, and copper 1. I was more worried about the this right here. By the way, you do know on the test, if you don't know that, you get the whole thing wrong. You don't get partial credit. It's like, well, I got the name right here, but you got to have this. That's part of it. Okay, what is the name of the following compound? Well, first off, is it binary? 1, 1. That means no poly, so you're not using the sheet. Okay, no, you shouldn't use the sheet at all in the Socrates. No, there was no polys. All right. However, as we look at this guy, we look at the location of your silver on the periodic table. So as we look for silver on the periodic table, we notice he is right here. Okay. Oh, he's in the transition metal, so that means he must get a Roman numeral. Oh no. Right. Well, hold on. Let's double check. Group 1, Group 2 do not get Roman numeral. Neither does aluminum, which is always plus 3, zinc, which is always plus 2, and silver, which is always +1. If we already know their charges, they do not get a Roman numeral. So this gets no Roman numeral. You just name it like you normally do. It should be silver oxide. Had to throw that one in there. Okay. Next one down the line.
Oh,
What is the formula of the following compound? Zinc chloride. Ooh. See if you got this one right. Well, let's take a look at our periodic table. Is he a transition? Yes, he is. However, he is one of the ones that always gets a charge of +2. Okay? So, and also here's the other thing. They didn't even give you a Roman numeral. That should be a hint right there. He doesn't get, a Roman numeral. Okay? Or he doesn't get a, he doesn't come with one. So anyway, So we just do it like normal. You got zinc, which according to your periodic table that you wrote this on, again, you're going to have to kind of know those three off the top of your head, but you'll know by that time. And then chlorine is a -1. You crisscross, and what do you end up with? A. Next one down, you got nickel sulfide. However, is nickel one of those that we already know the charges of? He's not one of these two, and he's not one of these three. He's right there. So we got to give him a Roman numeral. So, but this one's not too hard because it's a 1-to-1 ratio. So basically, what is the charge of the sulfur? It is -2. So, but the nickel, we don't know. And so basically, what -2 will give us 0? 2. So which nickel is he? He has a 2, which is C. Last but not least. All right, now this one's a curveball, but I think you can do it without my help. We didn't really go over it in the notes, but I assume you can go backwards. But let's find out. All right, so if they give you a Roman numeral, that tells you the charge of this guy, right? It's automatically a transition. If you see a Roman numeral, automatic transition. Okay, you shouldn't even have to look it up on the periodic table. It doesn't really matter. But that 2 tells you the charge of which guy? Titanium. So you write down titanium, who has a +2 charge. And then you got to figure out oxygen's charge, which you already know that by heart. -2. Crisscross, you end up with Ti2O2. However, can it be reduced or simplified? So it is TO. Well, T capital O, my bad. There we go. Which should have been A. These are the kind of questions, I promise you, that will be on the test. So this is a good way to kind of look at these. All right, so you know how you got to a transition metal? Now you should have been able to do these without any problem because they tell you the charge, that's a Roman numeral, you should be okay, all right? However, these guys, some people are having a little bit of trouble trying to figure out the overall charge. You take the charge of your second guy, and that's always going to be the negative guy, all right? Take the charge, drop the sign. So it's going to be negative, so just drop the sign. Bad handwriting, I know. The next thing you're going to do then is take that charge after you drop the sign and then multiply it. This is not an X, that is a multiplying sign. Multiply it by its own subscript. With me so far? Multiply by subscript. Okay? Then take it back to the left and then divide by the other subscript. Or the metal subscript.
give us an example.
He wants an example.
Are you talking about for B?
Yeah.
The column B or the column C? Or that'll work on?
This will work on everything. So like when you're trying to find the charge, like you're going to name. That's the hard part. Going from formula to name on this shouldn't be hard because you're doing the same thing. You're just using this as your charge. Okay? All right. So what's the charge of oxygen?
2.
All right, -2. Drop the sign, multiply it by its subscript right here. What is that? All right, drop the sign, then multiply. Just 4. Take that then, divide it by the subscript of the other guy. What's technically the subscript down here? 1. So divide that by 1. Guess what your charge is? Manganese 4. I'll do it again on another one. Tc. What's the charge of phosphorus? -3. Drop sign, multiply by its subscript. 3 times 4.
12.
12.
Divide that by 3.
4.
Tc4. Do it again.
So that's where you put the Roman numeral as a 4?
Yeah. So this should be a 4. This should be a 4 when you wrote it in. Here's another one. This one was another little typo, but we'll fix it. Br2. What's charge of Br? -1. Multiply by 2. 1 times 2.
2.
Divided by 1.
Well, 2.
Roman numeral 2. That will work
Jeez.
every time. Just like that. Do another one up here. I'll do them all if I have to, because it's just that easy.
No, you won't do it.
-1. Drop sign. Multiply by 3. 3. Divide by 1. Every single time. I'll do one more. No, I'll do them all. No, I'm just doing one more. So Ni3P2. All right. Charge of phosphorus is -3. Multiply that by 2. That is, divide it by the other guy, which is 3. See how easy that is now? Okay. That's where we left off. So let's talk about now throwing in some polys. Now I'm going to do this without transition metals to begin with to make it a little bit easier, and then I'm going to throw the transition metals back in. Okay? So we're going to do without transition to begin with. Like, what is the main idea? And you've already kind of played with polys dealing with the cards, but now we're going to get specific. You'll notice that some of these guys, and if you have that polyatomic ion chart out, you can kind of see some of these guys. This is what's so easy about it, is that all these guys do is just say their name. Don't change their last name. Whatever their name is, the SO4 is a sulfate. So you just say sodium sulfate. Okay? MnO4, that's permanganate. You just say potassium permanganate. NO3 is nitrate. So, polyatomic ions, I gave you the chart that you have to memorize. In college, they expect you to memorize it, and that's one reason why we do that. Usually, I'd like to kind of let you play with it a little bit, but pretty much by Friday, after Friday, you're going to need to know them by heart. That's when I would say you need to know them, because if you try to practice these right for the test, guys, I'm sorry, it's going to hurt. You really can't derive things. I put every possible way you can mess up on the test, like as a choice. Okay, so anyway, the metal, if the metal is not a transition metal but has a poly, this is the scheme of what we're going to go by. You name the metal, just like normal, just like you did with binary, but except for the polyatomic ion, you just say their name. Okay, and that's when you kind of glance at the chart. So today, guys, please look at the chart. It's actually, this will help you actually practice them for your quiz. Okay, so go ahead, take time right now and name these following guys. I gave you a quick rundown. Let's see if you can actually do that. Some of these we actually already talked about, like just now. First one you should have got was sodium sulfate, potassium chlorite, sorry. I always like to try to say that, but Anyway, calcium cyanide, sodium hydroxide, lithium carbonate. Most people have trouble with the CLOs on the quiz because they get them all confused. I usually try to tell people to practice those separately. Again, if you're trying to start memorizing these, I will warn you, the 8s have nothing to do with the how many O's you have. As you can see up here, sulfate has SO4, okay, and it still says 8. This one has CO3. It still has 8. So don't go by that, okay? Yes, technically, the more O's you have, the more likely you're going to say 8. That's really the only hint I can give you. Okay, that's pretty much all I can do. There is a reason why they do it, but if I tried explaining it, it would take a whole nother day, and even if I did, there's no 100%. It's just easier, honestly, guys, to memorize these, to be honest. When we get to acid-base chemistry, it'll make a lot more sense. But until we get there, there's nothing I can do. All right?
I thought it was perchlorate.
For which one?
KCLO.
Do I have it?
I see the 3. I put the 3, but I didn't see hypochlorite.
Right. So as they go up per does mean more oxygens when they throw that up there. If you ever see hypo, that means it's missing some. So hypo means it's going to be lower, like if you're hypoglycemic. Oops, sorry. You have a low blood sugar. So when you see hypo, that means less oxygen. So if you ever get per and hypo mixed up, just remember hypo is the lower.
What is it called?
Hypoglycemia?
Like when you got heart. No, it's like blood pressure.
Oh, hypotension. Yeah, hypertension is high blood pressure, hypo is low. And that makes sense, though, because perchlorate, more, higher, that kind of thing. I didn't ever notice that. I'm glad you said that. All right, now try doing it backwards. What? In other words, cover up these, and now try going back from the name to these guys.
We already know what it is.
I know you know what it is, but what if I just gave you this and not this? Ooh, what do we do? What do we do? Put it around the outside. They just didn't because there's a 1 out here. If there's ever a 1 for the poly, they usually don't give parentheses. That's the only time they never do it. So I'm telling you, you could do it either way for the parentheses part. But you have to do it if it has anything greater than 1. Okay? Okay. Now let's kick it up back to where we were talking about again. Still talking about polys, but now let's actually talk about with the transition metals. Okay, you just did transition yesterday. The same rules apply, except now you just got to look at your polyatomic ion chart and deal with the other guys. So if it has a transition metal, you'd still do the same thing. Exact same thing. Find the charge of the metal, represent it with a Roman numeral. All right, so now let's try some of these guys out. Now let me give you a rundown. All of these are transition. So you're going to have to figure out the Roman numeral of this guy. All right, let's see how y'all did. Okay, so we already did the first one together, which you take the charge, multiply, divide by that. If you take the charge this one, this is -1 times, well, technically what's down here? Imagine there's parentheses around this. 1. 1 times 1 divided by 1. 1. Copper 1 hydroxide. Charge of CO3 is -2. So 2 times 2, 4, divided by, do you deal with anything with this 3? No, it's just part of the name. ClO3, right, that's going to be chlorate, has a -1 charge. 1 times 2 divided by 1, 2, just like the one up here. Same thing down here, SO4 has a -2 charge. Are you going to multiply it by the 4? Nope. That SO4, that 4 is part of SO4, which is sulfate. Imagine, again, if they don't draw parentheses, you might want to draw them so you know what to multiply by. Again, that is just a trick I do. So that should be right here. Just because there's a 4 here, don't assume that everything's fine. But anyway, all right, so there's actually a 1 on the outside. So 2 times 1 divided by 1, cobalt 2. Okay? The main thing people have trouble with is the whole, be sure you write parentheses around some of these guys when you're trying to work these out.
How will you know if they need parentheses?
Well, count them. How many elements are up there? 1, 2, 3. 1, 2, 3. If you got 3 or more, you have a poly. And so I will tell you, 99% of the time, it's going to be the guy on the right side. So anyway, I'll have it on the side here. So again, as you go through each one of these, when you get to a problem where you're naming one of these guys, remember to cover up the answers and don't try to overthink it. All right, number 1. This one is actually a concept question. When atoms gain or lose electrons, they should even add the word share in there. They're trying to satisfy what rule? Is going to be the octet rule. It's the only rule we have talked about lately. All these others, Hess, we ain't even going to talk about Hess's law. There's no such thing as the valence law. And also Hund's rule was something y'all did back in Unit 2. All right, number 2. What is the name of the following compound, CuS? First thing, is there a poly? No poly, but is there a transition? Okay, so notice what I'm doing now. Every time I'm answering one of these guys, I'm asking 2 questions before I even begin. 2. Number 1, is there a poly? Number 2, is there a transition metal? Okay, notice I'm asking those every time before I begin. That might be something to write down, because the sheet I'm about to give you, you need to ask that with every question you do. Is there a poly? Is there a transition? Okay, if there's not, you just do a basic naming. So this one's like yesterday's work. We're trying to figure out this guy's charge. We know it's going to be copper, And what will we say for S over here? Sulfide. Sulfite would be SO, well, here it is right here. SO3, and then sulfate would be SO4. So it's neither one of those guys. Okie dokie. So now we got to figure out the charge. This is quick and easy. What's the charge of sulfur?
2.
-2. So -2 times 2 divided by 1. That'd be 4. Now find your answer that coincides with this. A. That is correct. All right. Moving on to the next guy. This one, ask yourself the question now. Number 1, is there a poly? Yes, there's a poly. Is this a transition? No. So no Roman numeral, but you do need to go with the name here. So how does this work? Well, each one says their name. So you got potassium. And the next guy, MnO4, if you look on your chart, which you should have memorized by now, but if you didn't, it just says its name. That's it. Per man, gan, 8. I know. Wait, is there E? No, there is no E. Okay. And so which one is that? C. Beginners want to go and pick like B because it's potassium magnesium oxide, manganese oxide. Yeah, right. Next guy, I mean, sorry. I don't know what that was. The gum got my way. Anyway, number 4. What is the name of the following compound? MgBr2. Okay, ask yourself the question. Is there a poly? No poly. Okay. Is there a transition? No. Okay. So we just name it normal. Okay. So it's manganese. Is that magnesium or manganese? Magnesium. And do we do bromine? Bromide. Oops, I capitalized it. Yeah, I know. Oh, they did on that one. Uh-huh. So none of them are right. No, actually, let's just go with C. Yeah, I have to go back and change that. So do the next one. We're going backwards here. Silver nitrate. Ask yourself the question, is there a poly? Yes, there is a poly. So we know that poly is NO3. What charge does that poly have? Negative. Well, I always have to look for it. All right, but silver, is that a transition? No. Well, it is a transition, but does it get a Roman numeral? No, he's one of those exceptions. Because what is his charge always going to be? +1. Crisscross, 1-to-1 ratio, you should just get regular old C, AgNO3. You could put parentheses around it, you know, when you do crisscross and get AgNO3, but they didn't have that option. But either one would be correct. I will never put both of those choices down and make you choose, okay? So don't think I'm going to, you know, that's just horrible. All right, moving on. Number 6. What type of bond does the following compound have? LICL. Well, you can go ahead and ask yourself this without doing any of the polar, nonpolar stuff. All right? Is this a metal?
Yes.
Is this a nonmetal?
Yes.
What type of bond is that? Ionic. You could go through and subtract electronegativities, but if it's metal plus nonmetal, we're going to say that. You should never pick metallic because there is no bond for that. All right, next up. What type of bond does HF have? Well, you got to subtract their electronegativities. And again, on your periodic table, I do not have mine up here. Actually, I do. Hold on. It's just out of reach. So when we look at this one, fluorine has a 4.0, hydrogen has 2.1. So what is 4.0 minus 2.1?
3.9.
Minus
Oh, 1.1.
1.9. So you got to remember the range between each one of these guys. I'm just going to remove this paper now since we're not doing polys. So you got to remember what the range is. If it is, let's say, greater than 2.1 or greater than, it's ionic. Polar is 0.5 to 2.0. And then polar is going to be the, well, hold on, I did it backwards. Less than or equal to 0.4. indifference. Okay, so which range does this fall into?
B.
It's going to end up being B. There is not one for metallic. The what?
I have a question.
Yeah.
How do you get 0.5 and 200
That was notes y'all got to know for polar and nonpolar. Like y'all got to know those ranges. Like they won't be given to you. It's in your notes. Next one. This is O2. Automatically, you could just subtract the electronegativities. 3.5 minus 3.5. But 3.5 minus 3.5 equals what?
0.
What range does that fall into? Nonpolar. I could just repeat them over here again. So I gave you an example of each way I could ask that on the test: ionic, polar, nonpolar. If you're missing out on the ranges on those, be sure to look over in your notes, because that's the only thing I'll ever ask you is like how to do that. And I'll ask it just like that.